Welcome to Evidence Mastery with Dr. Massoud Toussi. Today, we're diving straight into an absolutely crucial explainer on RWD pipelines and architecture. You know, turning raw, messy real-world data into analytically ready real-world evidence? That's not just some magic trick. It's a highly engineered, continuous process. As our healthcare systems pump out data at this unprecedented velocity, volume, and variety, the architecture we use to process it literally makes or breaks its fitness for purpose. So let's get right into how we engineer this massive flow to generate that regulatory-grade evidence we all need. Okay, here's our roadmap for this journey. We're going from the factory floor all the way to the dashboard dials. We'll hit the 4 pipeline stages, look at data lineage and versioning, compare architectures, specifically lake versus warehouse, talk about reproducible data engineering, and wrap up with monitoring operational metrics. Let's jump in. Starting off with Section 1, the 4 pipeline stages. This is the canonical flow for transforming those disparate clinical records. To handle the inherent messiness of clinical and administrative data, your pipeline generally needs this crucial horizontal flow. First up is ingestion, where we actually extract the data. Next is staging, holding it safely in isolation. Then comes transformation, which is where the heavy lifting happens, translating it to standard models like OMOP. And finally, analytics, where your data is highly structured and fully optimized for those complex epidemiological queries you're running. Let's zoom in on that very first step, ingestion. Traditionally, we rely heavily on batch ingestion. This is exactly what it sounds like. Data is collected and transferred in discrete, scheduled chunks. Think of your classic nightly or weekly historical claims extracts. But here's where things get really interesting. Contrast that with stream ingestion. In this setup, data is transferred continuously, right in near real time as it's generated. This is becoming absolutely vital for handling the modern flood of data we see from rapid psychopharmacovigilance or high-frequency wearable sensors. Moving on to Section 2, data lineage and versioning. And listen, this isn't just a nice-to-have, it's a strict regulatory imperative. Because if you can't trace your analytical results all the way back to the source, your submission is just sitting there, highly vulnerable to regulatory rejection. To put that in perspective, the 2018 FDA framework for the Real-World Evidence Program makes this an explicit mandate. They demand robust end-to-end data provenance. Without it, how can an auditor possibly verify that your specific patient cohort was derived using the correct validated logic? They simply can't. So, what's the crucial technical property that keeps us safe here? It's called idempotency. It's a bit of a mouthful, but idempotency basically guarantees that applying an operation multiple times gives you the exact same result as applying it just once. In plain English, it means if your pipeline crashes and restarts, it's never going to silently create duplicate records or corrupt your dataset. It's an absolute lifesaver. A perfect example of this in action is the FDA Sentinel initiative. This is a massive, proactive national surveillance system. Now, they can't physically centralize all the raw data across their whole network. That would be impossible. Instead, they use a common data model and distributed queries. By rigorously versioning both their local CDM builds and the central analytic modules, investigators can trace any safety signal directly back to the exact query version and the specific monthly data refresh. It's a brilliant case study in how distributed lineage maintains total auditability. All right, Section 3, architectures, lake versus warehouse. Let's take a look at the actual storage facilities that govern and secure our data. Historically, we were forced to choose between 2 paradigms, right? On one hand, you have the data warehouse. This enforces a very rigid schema on write. It's highly optimized for incredibly fast, complex SQL queries, but it is notoriously inflexible and super costly if you're dealing with unstructured data. On the other hand, you've got the data lake. This uses a flexible schema on read approach, which is awesome for storing vast amounts of raw data, like clinical notes, but as we all know, without strict governance, a data lake can very quickly turn into a murky data swamp. But thankfully, we now have the modern gold standard, the data lakehouse. This is a hybrid architecture that basically gives us the best of both worlds. It combines the low-cost, flexible storage of a data lake with the rock-solid ACID data management and performance of a warehouse. It handles everything, from unstructured EHR notes to your highly curated epidemiological tables, all in one place, effectively eliminating nasty data duplication. When you look at this comparison matrix, you can really see how these 3 stack up.
While the Lakehouse clearly shines for end-to-end RWD pipelines by handling diverse data formats and approaches, there is a catch. It does require some highly specialized engineering expertise to implement and maintain properly. It's not exactly a plug-and-play solution.
Section 4, Reproducible Data Engineering. This is all about ensuring your pipeline produces the exact same output every single time. Gone are the days of relying on fragile manual scripts and basic cron jobs. Professional data engineering today demands modern workflow orchestration. We're talking about tools like Apache Airflow, Dagster, or Prefect. They use what we call directed acyclic graphs, or DAGs, to map out your task dependencies visually. They come baked in with automated exponential backoff retries for when the network inevitably hiccups, they fire off immediate alerts to your engineers, and they keep detailed logs capturing row-level metrics and exact code versions. And that brings us to our final stop, Section 5, Monitoring Operational Metrics. Because a well-architected pipeline is definitely not a set-it-and-forget-it system. You have to keep an eye on the dials. Operational metrics like latency and data refresh cycles absolutely must be tailored to your specific scientific use case. Take pharmacovigilance, for example. You need low latency there, hours to days, and your critical metric is watching for data volume drops to ensure you aren't missing adverse event reports. But if you're running a retrospective cohort study, weeks to months of latency is completely fine, and your focus shifts to something like code mapping success rates. Now, here is a really provocative question for you. How do we detect and stop silent failures? You know, those terrifying moments where data gets corrupted, but the pipeline completes successfully anyway. Just imagine a source system randomly changing its date format from month-day-year to day-month-year. The pipeline itself won't crash, but your patient timelines are suddenly completely shifted and useless. The only real mitigation strategy here is building automated data quality gates right into the flow. You place these before the data is ever promoted to analytics. We're talking volume checks, like, hey, did our unique patient count just drop by 15%? And distribution checks, like, is the mean cohort age suddenly 150 years? If a gate fails, it immediately halts the process and alerts the team. It stops the bad data in its tracks before it can poison your real-world evidence. To wrap up this explainer, the foundational scaffolding we've talked about today is detailed much further in my upcoming book, Real-World Evidence, Sources and Solutions, which will become available later this year. Getting this architecture right is absolutely essential for professionals across pharma, healthcare, and regulatory bodies. Thank you so much for watching, and please make sure to subscribe to the Evidence Mastery channel to see many more explainers diving deep into real-world evidence and real-world data. See you next time.